Hello everyone, I'm Zhouyuan from Google. Today, I'm presenting the paper Training Neural Networks Using Features Replay. This is joint work with Professor Bing Gu and Professor Heng Huang. The success of deep learning depends on three important factors: big model, big data, and big computing. In terms of big model, let's take the ImageNet classification as the example. In the figure, we can see that from GoogleNet, which had about 4 or 5 million parameters, to the MBZUAI, which had about 600 million parameters. The top-down accuracy on ImageNet dataset can be improved from 75% to 85%. We can see that the bigger model we have, the better performance we can achieve. To optimize the neural networks, we need to use the stochastic gradient descent. Let's take the 3-layer neural network as an example. Each layer, we have the parameters W1, W2, and W3, and loss function L. As long as we compute gradients regarding to the weights in different layers, we can use the SGD to update the model. To compute gradients for deep neural networks, we use the backpropagation algorithm, or BP algorithm. The BP algorithm has two passes: the forward pass and the backward pass. In the forward pass, the input H0t is forwarded from layer 1 to layer 3, and we have loss function after the forward pass. In the backward pass, different layers will compute gradients regarding to its input and model weights. So in layer 3, it will compute gradients regarding H2t and W3t. After the computation in layer 3 is done, it will pass partial LT or partial H2t to layer 2. Then layer 2 compute the gradients of partial LT over partial H1t and partial LT over partial W2. In the computation, it will require the gradient result from layer 3, which is partial LT over partial W over partial H2t. After the computation in layer 2 is done, layer 1 will receive the result from layer 2 and the compute gradients regarding to W1. So this is the process of BP algorithm. However, there is a problem in the BP algorithm, which is called backward locking. The backward locking means that when layer 3 is doing the computation, layer 1, layer 2 will be idle because the computation in layer 1 and layer 2 are dependent on the output of layer 3. Because of this problem, if we split layer 1 and layer 2, layer 3 to different devices, we cannot parallelize the computation in different layers because of the backward locking problem. To solve this problem, we propose the decoupled delay gradient. The idea is very simple. We just need to make different layers compute gradients using different samples. For layer 1, it use the samples from time step A, and layer 2, it uses the samples from time step B, and layer 3 using samples from time step C. And as long as A not equal to B and not equal to C, the different layers are independent from each other. The difficulty is that when layer 1 want to compute gradients regarding to the partial LA or partial W1, it need the partial LA or partial H1A should exist in layer 1. Layer 2 also have the same problem. To solve this problem, we just need to make A smaller than B and smaller than C. For example, if we make A equal to times T minus 2, B equal to T minus 1, and C equal to T. Let's take the figures as example. In the forward pass, the input H0T is forwarded from layer 1 to layer 3, which is similar to the BP algorithm. The difference happens at the backward pass. In the backward pass, layer 3 will compute gradients using samples from time step D, and the result, partial LT over partial H2T, are computed. Then it will pass this value to layer 2. Layer 2 In layer 2, instead of computing the sample gradients using samples from time step t, layer 2 will compute gradients using samples from time step t-1. In this way, because the partial L t-1 over partial H2 t-1 has already been received from layer 3 in the previous time step. So at time step t, layer 2 and layer 3 are independent from each other. Similarly, in layer 1, it just need to use the results partial L t-2 over partial H1 t-2 from layer 2 in previous time step, and the computing gradients using the samples from time step t-2. In this way, layer 1, layer 2, and layer 3 are computing gradients using samples from different time steps, and they are independent from each other at time step t. So suppose we have a 12-layer neural network, and each 3 layers are placed on different devices. So there are 4 devices or 4 GPUs. By using the decoupled delay algorithm, module 1, module 2, and module 3 can compute it in parallel. However, there is one issue, which is by using the BP decoupled delay DDG algorithm or decoupled delay gradient algorithm, layer 1, layer 2, layer 3 should store the activations of the previous time steps, which is very space consuming. To solve this problem, we propose to use the feature replay algorithm. So for example, in module 1, instead of storing the activations in different time steps, module 1 will, in time step t, to compute gradients using samples from time step t-3, you just need to input the input of the module 1 h0 t-3 to the module, and using the model weight wt to recompute the activations at layer 1, at layer 2, and layer 3, which are to the h1t, to the h2t, and to the h3t separately. In this way, we can reduce the space complexity to big O L plus k square, where the L means the number of layers and the k means the number of devices, because the number of layers are really much bigger than number of devices k. So the space complexity is very similar to the memory consumption of the BP algorithm. In the paper, we also analyze the convergence rate of the proposed algorithm. We propose to analyze the convergence, we propose a new sufficient direction assumption. We assume that the expectation of the gradient computed using the feature replay algorithm is in a positive direction, which regarding to the sigma, some constant sigma, and it is bigger than 0. To verify the assumption is reasonable in the deep learning, we realize the variations of sigma in different modules on the ResNet 100.01. In the figure, there are 2 observations. The first is that all the sigmas are bigger than 0. And the second, in the sigma in the module layers is smaller than the module layers, higher layers in the beginning of the training. However, after the optimization, the sigma value of different modules will be very close to each other and very close to 1. So by using the assumption, we can prove that the feature replay algorithm can converge to a critical point with the sublinear convergence rate, which is similar to the normal stochastic gradient descent algorithm. In the paper, we also execute extensive algorithm experiments to verify the performance of the feature replay algorithm. In the first figure, we can see that feature replay algorithm converges very similar to the BP algorithm, and if we increase number of GPUs, we can reduce the training time significantly. If the number of GPUs is 4, with the computation time of feature replay algorithm is just about half of the training time of the BP algorithm. In the figure 2, we also compare the memory consumption for different algorithms, BP, DDG, and the feature-able FR. We can see that feature-able algorithm consumes very close memory as the BP algorithm. In the table, we conducted experiments on different datasets and different modules. In the table, we can see that feature-able algorithm can achieve a better solution than the BP and DDG algorithm. We suppose that we suppose that the reason for the feature-able algorithm better than the BP algorithm is that in the training, the noise can serve as some regularization in the training, so it could improve the generalization performance. In summary, to parallelize the training of the big model on multiple machines, first, we break the backward locking in the BP algorithm. Secondly, we reduce the memory using feature-able algorithm. The codes are available in this website, and thank you very much.